I've occasionally heard that pitched roofs only work for small buildings such as residential buildings like a house. And as that building gets larger and becomes the size of a large commercial building, then a pitched roof will no longer work because you'll have too much wasted attic space. That attic is defined as the space that is above the walls and below the roof. And for the most part, it's considered wasted space because it's full of trusses, so it will have little, if any, commercial value. So my question is, as a building grows larger, so as you go from a small residential building to a large commercial building, does that wasted volume in the attic increase or scale up in proportion to the rest of the building? So for example, if you have a building with 10 times the livable volume, does that mean you're going to have 10 times the wasted volume in the attic? Or are you going to have 100 times the wasted volume in the attic? So that's what I'm going to show here. So pitched roofs are better because they work better for snow shedding and they leak less than flat roofs. But you won't be able to have a pitched roof if the construction cost is too much for all that wasted space. I'm going to use an angle of 45 degrees for our pitched roof here. I'm using that angle for two reasons. First off, it just makes for simple math. Okay, that's really the only reason, but also at 45 degrees, that's considered an optimal angle for snow shedding from what I read. Okay, so we have our little one-story house right here with dimensions 1 in each dimension. The livable area, A sub L, will be d squared, d times d. Livable volume will be d cubed, d times d times d. The wasted attic volume can be calculated a couple of different ways. You can take the area of this whole triangle times the depth, or you can take the area of half the triangle times the depth and then times 2 for the other half. And that second option is what I went with. So we'll go over 1/2 d and then up 1/2 d, and that will be 1/2 d times 1/2 d. That will give us the area of a square, but we want half of that. So we multiply times half because we want the area of a triangle. Multiply that times d for depth. Multiply that times 2 for the other side. So we have the area times the depth times 2 for the other side. This reduces to 1/4 d cubed. That is the wasted volume in the attic, or mostly wasted volume in the attic. You can use it sometimes for small rooms or storage, but a lot of times it's not used for anything at all. I chose a prism roof, which is just a long triangle, but if you want to go with a pyramid roof, you'll pretty much get the same results with the math. So a prism roof will be 1/4 d to the third, or d to the third over 4. A pyramid roof will be d to the third over 3. And that's because the volume of a pyramid is 1/3 times length times width times height. But if all these dimensions are the same, we can just call them all d. So we end up with d to the third over 3 compared to a prism roof, which is d to the third over 4. So here's an edit for a small correction. The formula for a pyramid is 1/3 length times width times height. The length and the width are d, so we have 1/3 d times d. For a 45-degree angle, the height will be 1/2 d. So this simplifies to 1/6 d to the third. So a pyramid roof is slightly more efficient than a prism roof, but not by much. And I imagine there's some extra work and expertise involved in making a roof a pyramid instead of a prism. So now let's scale up our building from our small residential building to a large commercial building. Yeah, maybe you can see right away that in proportion here, this wasted attic space or this wasted attic volume is much larger than the livable volume right here. That is, if our commercial building is only one story, like our little residential house. If your commercial building goes up to several stories, so it maintains that cube shape, then the wasted volume of the attic will scale up in proportion to the livable volume of the rest of the building. But if it's only one story, then that means our dimensions will be d times 1, or just d squared, which is the same as the livable area. I'm only doing one story here because most commercial buildings are just one story. Take a ratio of our wasted volume over our livable volume. That'll be 1/4 d to the third over d squared. This reduces down to d over 4. If we want to maintain the cube shape of our building, then we'll have the wasted volume is 1/4 d to the third, and the livable volume will be d to the third. So you'll have d to the third divided by d to the third, and everything will scale up in proportion. And that's because d to the third divided by d to the third cancels out. We just end up with 1/4, which would be the same ratio as our small residential building. If you want to, you can stop the math right here and you can see that the wasted volume scales up by the cube, but the livable volume scales up by the square. So we have a cube divided by a square, which means that the wasted volume will grow and outpace the livable volume as that building grows in size. So in other words, as that building gets larger and larger, you're going to spend a lot more construction cost on the wasted volume compared to your livable volume. This fraction right here reduces down to d over 4. And if you want to get technical about this, you can take the limit as d approaches infinity. So each dimension will have infinite units, meaning it'll have infinite length in both dimensions of our building. So it'll be a very long building and a very wide building. Take the limit as your dimension approaches infinity. You end up with the limit as dimension approaches infinity of d over 4. So that equals infinity. This means you will have infinite wasted volume and 0 livable volume. And of course, even if the dimensions of your building don't go to infinity, because that's not going to happen in real life, this shows the trend that as the building gets larger, you're spending more and more money on wasted volume and having less and less livable volume. The reason I chose infinity right there is because I learned a long time ago, way back in school, that if you really want to get an understanding of a concept or get a really good intuitive feel of a concept, it often helps to take the idea to extremes. So in this case, I'm taking the length of my building to extremes by making it infinitely long. So I think it really helps give an intuitive feel of the trend on how that attic space increases compared to the livable space. And next page. Instead of a ratio of a wasted volume over a livable volume, you can do a percentage of wasted volume, which will be your wasted volume over your total. Total equals your wasted volume plus livable volume. Go through the algebra here. You can pull out a d squared right here. So then this d to the third divided by d squared ends up d. So you have 1/4 d over 1/4 d plus 1. Take the limit of that as your dimension approaches infinity. So in other words, as the building grows infinitely large, then you'll end up with infinity over infinity plus 1, which will equal 1, which equals 100% wasted volume. I'm going to touch on the square cube law here because I figure it matters. You can see my other video I did on the square cube law if you're interested for more details. So let's say we have a ceiling beam or a beam that goes across and supports the ceiling in our house. We can just pretend it's a 2x12, so it's 2 inches thick and 12 inches high, and let's say it's 10 foot long. If we want to make our room twice as large or twice as long, this beam will need to be twice as long. But as that beam gets longer, there will be increased torque on it or increased bending in the middle of it. So we need to keep the dimensions the same. So if we take this 2x12 and we extend it out twice as long in the x direction, it has to be twice as tall in the y direction and twice as thick in the z direction to keep the same dimensions. 2 times 2 times 2 is 2 cubed, so we're looking at 8 times the material or about 8 times the cost. And in addition, this will drive up the expertise needed because any kid can build a doghouse, but it takes some expertise to build a residential house for people. And if you want to make very large rooms with very large ceiling spans or beams or trusses, that will take even more expertise. And you could count up your 2x12s right here. We have our original 2x12 right here. So 1, 2, and then it has to go 3, 4 right here. And then you're gonna have 5, 6. That'll be 7, and then 8 will be hidden behind it. So basically we need 8 2x12s to make our beam twice as long to keep it as the same dimensions. And as I often say, I'm not an expert on any of this stuff. I was just curious how the attic volume scales up with the rest of the house. So I thought I'd put some equations together to see what I could figure out.